Hello, welcome to Engine's Access the Expert. We'll be starting in a moment. I just want to allow everybody to be joining us. So give it a couple of moments and we'll be starting, okay? Hi. Hi, gentlemen. We'll be starting in a moment. Welcome to Engine's Access the Expert, enable modern product development, leveraging essential technology. We'll be starting in about a minute or two. We'll just allow people to get on. Again, hello. As you're joining on, we're allowing a moment for everybody to jump onto this call. You are with Engen Access the Expert. We'll be starting in a moment. Again, I just wanted to remind everybody, we'll be starting in a moment. We're just allowing people to jump on, so give it about a minute. Almost there. We'll be starting in any second now. I just want to say hello to everybody. My name is Frank DeFalco, not NGen Webinar. I'll be hosting and moderating this event. Today, we are happy to present the Access the Expert, enable modern product development by leveraging essential technologies. We have two experts here to discuss this from CAD Micro Solutions. We have Deep Singh. He's the VP of Advanced Manufacturing with CAD Micro Solutions, and we have Mohsen Tayefe. He's the National Strategic Business Manager, also with CAD Micro Solutions. So we look forward to this great presentation by these two knowledgeable individuals, and we are about to start. So why don't you take it away? Go ahead. I will bow out.
Thank you. Hi, everybody. Really nice to be here and having our discussion today around enabling modern product development by leveraging essential technologies. My name is Deep Singh. As Frank said, I'm the Vice President at CAD Micro Solutions, overseeing the advanced manufacturing and additive manufacturing portfolio of our business. Looking at technologies like 3D printing, post-processing techniques, software implementation, services support. Those are the type of things that I look at. And I'm joined here with my colleague, Mohsen Tayefe, who's our National Strategic Business Manager. So I'm going to pass it to Mohsen for an introduction. Thank you.
Thanks, Deep. Hello, everyone. I'm Mohsen. I'm simulation expert, and today I will present some of the simulation applications for enabling 3D printing to be more applied. And during the presentation, we will start with introduction about CAD Micro Solution as a great company that helps a lot of industries in Canada. And then we will go through some challenges that companies are seeing in these days, different product development phases, and we heard a lot about like many different technologies regarding additive manufacturing. So Deep will help us to understand which one is good and basically how to deal with selection of technologies. Also, we will have live demo and virtual showroom at the end of those presentations. I will also discuss about advanced design and virtual validation, very interesting topics about including new technologies in the design process, collaboration between different departments, and how these are all together essential technologies to make 3D printing be more effective and used more. And at the end, we have Q&A. We can answer any questions you guys have. I pass it back to Deep.
Thank you, Mohsen. So some of you in the audience already know about CAD Micro. For those that don't know us that well, we're a Canadian value-added reseller company established since 1984. So we've been in the Canadian market for some time. We have offices from coast to coast covering the west, the central, and the eastern part of Canada. We enable our partners and our companies that we work with by leveraging the latest and the greatest technologies like 3D printing, CAD softwares like SolidWorks and Dassault System products, 3D metrology, and immersive technology like AR, VR. We're a value-added partner, so we want to provide value to any projects that we get in, and it's been working in sense of those collaborations that we're doing. So the areas that we look after, and where we can help. So we say, okay, the center point for any of our discussions really, how do we help our companies, partners enable innovation, right? And there's a range of Industry 4.0 technologies that are available that allow you to enable innovation. And it all starts from sort of the heart that we feel it's leveraging the digital twin data. It's the stuff like, you have your CAD packages, or you have your 3D scan data. What can you do with that? How do you maximize your return of investment on investments that you already made around digital twin? Additive manufacturing, 3D printing is part of that. There's simulation, which is another component, but there's a range of different technologies that go in, and we're going to try to touch upon some of those today in our discussion. Before we go further into our dialogue, these are some of the questions I want people to sort of think about. Are these the challenges or issues that you're having in your business today? We understand that there's a growing demand of changes required by customers. You might be working on a project, and then throughout your project design development stages, customers are constantly challenging in terms of design changes and modifications to meet their requirements. Are you finding that to be a challenging task in your product development, that your customer requirements are changing? Do prototypes, short-run production parts, manufacturing aided tools, spare parts inventory, are these representing a significant cost in your business today? Many times I'll go over to companies, and this is prior to the pandemic. Now we're doing a lot of virtual conversations, but if we go to a factory or a facility, they have inventories that are locked, $3 million, $4 million worth of parts, or even more in some cases, that are just there to repair their machines when the machines go down. So for those unpredictable downtimes that they occur, right? So there's significant cost that goes into holding that inventory. So think about those. Think about the prototype runs that you do. How many manufacturing aided tools do you have to deploy to get to your finished product, right? So those are type of areas where you might have some cost. Would you like to minimize your customers' risk before they invest in tooling? So those are the things. Are those values you're offering to your customers today, or are those values you want to offer to your customers down the line? Are you not aware of different design or simulation technologies available for additive manufacturing or advanced manufacturing, right? So would you like to learn more about those? Did you ever have a delay in your project deadlines because there was manufacturer part defects? How often does that happen in your business, right? Are you looking at implementing a complete end-to-end Industry 4.0 solution to decentralize your supply chain processes? Now that we're all sort of stuck in this challenging time, and we're trying to come through that as society due to the pandemic. Are you noticing those pandemic caused issues disrupting your workflow, and your supply chains are getting complex? So those are the questions I want you to think about. If those are some of the challenges areas that you have today, then definitely this is an area where we can help you, or you might find some value from working with CAD Micro. But what we do see, companies that we work with have different priorities and challenges on daily business. And I try to characterize them in three different areas. You got your top business issues today. And some of them include, you have improvement in workforce productivity. Productivity is always on the top of the list for businesses to continue to improve. And you have a reduction in your operation cost that is, mandatory. And we sort of, in my initial conversation, I asked, are you having those inventory costs that are adding up? Those are part of your capital costs. Those are your, you have your operating costs as well. Increased profitability is always on the chart for everybody. Every company leader that I've spoken to wants to increase their profitability. That's always a top priority. Improving quality of the product and processes, because that's how you're going to maintain your customers and your credibility in the market. Improving speed to the market. The faster you get to the market, there's benefits to that. You're able to recoup your cost faster. You're able to get market validation faster. And managing uncertainties, unplanned downtimes, right? How do you prepare for that upfront? So those are some of the top issues and challenges that we're noticing companies have. And then from their manufacturing priorities, they want to get to the market faster. You want to be able to be flexible as much as possible for your customer. You want to be able to do modular designs, product life cycle management, all of those things that you're going to have manufacturing challenges. You want to be able to overcome those before you encounter those. And then the market volatility is certainly not helpful. Material cost continues to be a challenge. We get hit with tariffs and all sort of regulatory procedures. They become a problem. Labor costs, transportation is a big one, right? Like there's so much happening around it. Environmental laws are constantly evolving and changing, where there's a focus on sustainability for a couple of years now and still moving forward strong. So we have to look at that. Now, regulatory compliances, right? So there's a range of challenges. So it's not easy to do business in 2021, right? It's there's a lot of different priorities on the table. Everybody wants to succeed and do good, but to get to that, CEOs, manufacturing managers, the engineers, everyone that's involved in the operation are dealing with lots of different challenges. And sort of all of those challenges, they are tied to your entire product development stages, whether that's your pre-development phases, your development stage, or your post-development. And the complexity comes from many different areas. Your challenges with your customers constantly changing ideas, or production volumes and requirements and materials and so on. But when we look at pre-development stages, you can break them down into your concepts, into your prototyping stages, and a term called bridge production, where you're not at the complete capacity that you want to get to. You're just ramping up your production. So I would define that as bridge production. So that would be your pre-development stages. Then you get into your development. That's where you have your production. You got your hundreds and thousands and millions of parts that you're doing. And then it comes time where you have your post-development, where now the part that you were really excited about that did so well in the market, the curve starts to go down because better and more innovative solutions are coming to the market, or you're developing them. And this curve represents the volume in different stages, right? Your concept, your very early, very low volume. This could be your idea generation. This could be a sketch on a piece of paper. This could be your initial CAD model, but to get the concept, your volume is very little because you're making a lot of changes here. Then you get into the idea stage, and you're now developing your process. You start doing prototypes. This is again where design iterations are key to have a successful product. You get into your product manufacturing conversations, your engineering material conversations, and this is where again now the volumes are starting to incline because you're doing a lot of different testing to get things going. Bridge production, you're now reaching towards your production goal, right? You're doing a market validation. There's no point in making a million different parts if the market is not going to accept that, right? And to give you an example in this pre-development stages, think about potato chips. I think about a company like Lay's who fabricate potato chips, and they do lots of potato chips and millions of them, right? But before they roll it out to the market, before they get into the production and development, they do their design validation, their pre-development validation by printing plastic chips with different textures and patterns to see what kind of feedback someone's going to give them, because the tangible aspect, how you feel that potato chip, is really important, how it looks, right? They certainly don't produce potato chips that you can eat, not edible today, but when you're looking at design validation, the pre-development, that's where additive manufacturing is getting utilized. And then you go into the production run, and in some capacity, additive has come a long way. We think about, when we think about 3D printing, when we think about additive technology or essential technologies that we use, we think about a printer, or we think about a hot glue gun that just melts plastic, and that's one type of technology, and further in our discussion we'll see more. But there's a range of different tools available, and the range of different technologies available, and some of them are tackling these production volumes. And the production volumes could have a combination of your spare parts, it could have a combination of your pre-developed parts, and all of that is a mix where tooling might not be required, right? And then you get your spare parts aftermarket, as we sort of talked about. So this is, in a nutshell, sort of the product development life cycle stages that you would encounter. And the roles that get impacted are exactly the same. You have your general managers, your manufacturing managers, you have your engineers, and they all have different pain points, but they get divided into their categories, right? So the CEO is looking at growing the business, getting it to making it to be more flexible and agile for their customers. The manufacturing manager is looking at manufacturability of the design, which technology to go with, design iteration planning. So there's a lot that's on the plan. End-to-end control, you might lose out on that if you are not doing that in-house today, if you're not fabricating your own parts in-house today. And then the engineer, and I think this is where your some of your biggest cost driver are your how well your engineers are trained in certain technologies, because they're trained to design for that technology, right? So your cost, and I tell this to people all the time, I say, make sure your engineers have all the right tools, the skills, everything that they need to understand the technology that they're designing for, right? If you isolate them from that technology, then if they're not getting the exposure, then they might not be able to design for reducing your cost, right? And so that's where it starts from. And additive manufacturing helps in all these capacities. It helps you optimize your cost functional part if it's deployed properly. You're more flexible because the equipment can give you access to printing health parts, aerospace parts, all sort of range, but it's all through one technology. And freedom of design is the biggest enabler for that technology. So why 3D printing? Because I think it's going to help you in optimize your lead time, so you can go to the market and you can respond to the market quicker. Allows you to personalize. Personalize is a big element, right? 90% of the ear aids are 3D printed today. There's a lot of business happening in the world of medical devices. We see one of the Canadian company, Precision ADM, leading the chart with nasopharyngeal swabs that are, Canada, put the Canada on the map. So there's work happening in our own country where, personalization and rapid response to the market is happening. economical, and this I say it carefully because you have to know where to use the right technology, right? Additive manufacturing is not here to replace conventional technologies like CNC or injection molding. It is a complementary tool, and it's an ecosystem that we have to look at. It's not just a sector by itself, it's the entire ecosystem. And then the freedom of design, without compromising mechanical properties. Again, you got to really dig into your applications. So, there's some really strong evidence that this additive manufacturing is really helping. Last year, when everyone went under the initial lockdown, the stage 1, when COVID was first announced, we saw everybody across the world, not just in Canada, firing up their 3D printers, firing up their additive technologies, and creating a wealth of design and sharing these files. And there was personal protective equipment, there were swabs, there was ventilator parts. Not to say that traditional technology couldn't do this, but it was going to take traditional technology a very long time, and in terms of design iteration, in terms of developing these products. But with additive technology, you could have someone design a part. For example, the face shields, Canadian face shields in Canada, a lot of them were 3D printed initially, right? In millions, in volumes, in really high volumes. People across Canada geared up their production level printers and worked with authorities to get class 1 devices validated and certified and scale them en masse. So the technology, the additive, allowed the product development cycle to rapidly impact the Canadian and global market. The files were developed, the files were shared. You can modify them and you can make them, tweak them, and make it to your own liking. So a lot of that was enabled by additive technology. And it was all possible because of the enabler that's behind this whole infrastructure, and that's your Industry 4.0 capabilities. It's the ability to digitally share 3D CAD data. It's the ability to print remotely. It's the ability to work in security parallel so that your files are not jeopardized or compromised when they're transpiring. So a lot of that is driven by this Industry 4.0, and the Industry 4.0 is real. It's really happening. It's around us now, and there's no turning back. It's only moving forward. But how do you pick which technology is right for you, right? This is a question we get asked all the time, and this is a great graphic by Link3D guys that sort of shows you a range of different technologies and processes that are available out there. You got sheet lamination, where you might have sheets of composites or metal that gets fused together and then cut out into a shape. You have extrusion technology, which is where you're melting a thermoplastic through a nozzle and deposits layer by layer. You got vat photopolymerization with liquid resin that gets hardened with UV light. And by the way, a lot of development happening in vat photopolymerization around speed. It's phenomenal what you can do now in terms of how quickly parts can be produced for validation. Material jetting, where you're depositing very tiny materials, so nanoscale printing is now become possible. Powder bed fusion, this is where if you're running into the production batches, this technology has become a great enabler. Direct energy deposition, lots of rocket engines are getting direct energy utilization for metal 3D printing. That's happening. Cold spray is relatively new. It's a technology that's coming out where you're hitting with cold spray techniques for metal, and it's creating a near net shape, and then you go after and clean the shape. Binder jetting is getting a lot of attention these days. Again, it's come back. It's been an old technology around sand cores and sand casting, but now binder jetting is getting a lot of attention around metal, to be able to print parts that are held by metal powder and then sintered afterwards. So, where do you start? There's just so much. And I hate to say it, if you haven't invested in 3D printing today, you are a little bit late. You can catch up, but you are a little bit late because people are using this already, and they're finding success, and they're cutting their costs down, and there's areas where it can be helped. But this is another one. This is another great one by AMFG guys, where this is a landscape of different companies, from hardware, from software, from materials, post-processing, which banner, which logo do you pick? How do you select the right appropriate manufacturer that's going to meet your application requirements, right? It's very complex. And not only that, it's also about repeatability, reliability of the equipment. So don't believe everything that the sales guys will tell you, because it's going to be out there. There's lots of smoking mirrors, is what I say is in our sector. You can print these wonderful things, but then you really have to do your homework, and it's important that you partner up with an appropriate person to walk you through that journey or help you out. My conversation with people is usually, let's start with a functional part requirement. Don't just jump in that, hey, I'm going to get a 3D printer and then we'll figure out, or we're going to get some parts out, because printers will print, right? But what is your functional part requirement? What do you need the part to do? And it's really a conversation around part. It's not about your overall business. You have to look at it by part, because it's a right tool for the right job. Selecting a right OEM with the right printer, it's going to be around your application. And it doesn't have to be additive, right? The formative technologies, the subtractive technologies, and the additive, they all have an integrated role to play. You can't just stick with one. There's a right time for the right application. And you have to develop your own decision-making tree on how you're going to go about evaluating. But here's an example of how we look at parts when they come to CAD Micro. When we look at applications, initially we'll start by understanding, your current situation. Which stage of your product life cycle you're in today? Are you in the concepts? Are you in the end use? And you know what? The concepts are the easiest ones. The manufacturing aided are the easiest one. It's the production and the functional requirements. And more of our demand, more of our conversations are around functional. People are no longer just talking about prototyping. They are talking about end use. Here's how I make my part today. I need to make similar or better part. How do I get that? So we have to really dig deep into what is their current need, what is their what are the important properties for that particular application, and is that suited for additive manufacturing? Now, in many cases, we go straight from understanding those requirements and lining up the right additive technology. But it's important to have that background first. It's kind of like a chicken and egg question, right? You have to have an understanding of additive technologies, not just one, but a range of different tools, and then to be able to assess your parts and then say, okay, which technology is going to be best suited. So the right side actually comes left first, and then you have to have that on the right side as well. So the end-to-end additive processes are as critical as your part. So if your part meets the requirement, if you got your mechanical properties, you go about selecting your technologies. I have 3 technologies there, but you can have a range of them. And then you start looking at, okay, what is going to be my additive process, right? It's no different than when you do injection molding. You have your draft angles, and you have your runners, and you have to have post-processing to remove edges and deburr and so on. But in the additive, it's a different type. You have to understand what kind of software you're using to start with. How are you going to be able to build your part, pack your part, orient your part, and where is the time going to be utilized in that workflow, right? So understanding those softwares, is it going to be local? Is it going to be cloud? What kind of securities do you need if you're doing cloud? What kind of standards are going to be following? The process parameters are important, right? If you are going to be working with a certain material, do you have material parameters? Traceability in some applications might be important. Your feedstock standards might be important. And you know what? A lot of people say, and this gets advertised all the time, that there's a food grade or food safe material. And then you look at the process, and the process might not be. So you got to be careful that you're not just looking at one thing, you're looking at end-to-end solution. Then you get into is it going to be an open source system, or is it going to be a closed loop? They both have advantages and disadvantages. The open source allows you to reduce your costs. You can have different experimental feedstocks that you can work with. But when you get into the closed, but the disadvantage on the open loop might be that you don't have the material profiles on how the material needs to be cured or printed or sintered and so on. So there's going to be a bit of R&D, but it allows you to experiment. The closed loop might have a great solution. It's going to cost you more because the materials might be locked, but it is fine-tuned. It is, you're working with an ecosystem where you're going to press print and it's going to come out great every time. The really incredible thing that I'll show you guys in a bit, that I really enjoy, is the quality assurance applications that are starting to build in additive systems. So you can print parts, and there's AI-driven applications that will assess your part, how it's going to be, and adaptively change during the printing process. And then that leads to sort of the decision makers are going to look at your total cost of ownership and return of investment. What it's going to cost. That is if additive technology is suited. If you created a part that's best suited for additive technology, and if it meets your important properties. But let's say if it's not, then the things that you look at is, can this part be designed for additive manufacturing? Instead of having one part, instead of having multiple parts, can that be consolidated? Can you take advantage of simulation that Mohsen is going to talk about? Can you take advantage of lattice structures and have different behavior of your part happening? Or maybe you already have a part designed that's designed for a different set of technologies. Can you modify that for additive manufacturing, right? Are you able to make changes to that? If the answer is yes, then you still have life and you can go into the additive technologies and start exploring. But if the answer is no, don't waste your time. Move on to the different technology, right? And that's only going to come if you understand the additive manufacturing ecosystem. And to understand that, you have to be at the forefront and innovating and adopting to the technology so you can learn the pluses and the minuses, right? So I always say, it's a right tool for the right job. And I'm going to move over to like a virtual showroom, show you guys sort of a selection of different printers that we have and talk about those as we go on. But effectively, there's the right tool for the right job. And I wish I could have people come into our office right now and see this setup, but our marketing team is doing some great initiatives around putting everything online and creating a virtual experience. And you can visit this after. So let me switch over to my virtual screen. And Mohsen, if you can confirm, you can see the virtual screen.
Not yet.
Okay. Okay, you should be able to see it now.
Yeah.
Okay, so this is accessible, guys. You guys can go on showroom.cadmicro.com and you can look at these. And our goal was to create a 360 experience for you that you can go and learn about all the different technologies. So here, for example, we have a metrology station. But I'm going to start with this VAT photopolymerization technologies that we have in-house. So here's a technology called Formlabs. If you want to learn more about materials, you want to learn about different applications, you can click it. We try to make it as interactive as possible. You can download case studies, all sort of stuff. But this is a great technology if you're looking at affordable SLA for high accuracy, high resolution parts. A lot of medical devices are being produced by this. If you're looking for high aesthetics, if you're looking for elastic materials, right? Like if you want to simulate some of the behavior of flexible materials, SLA is great. So this is your Form 3. Then a company that we partner with is Nexa 3D, and these guys are really disrupting the speed on how quickly you get your parts. And I'll show you an example in my slide deck shortly. But effectively, instead of using a UV curing laser, you're using a LCD that projects the entire cross section of your part. So whether you have one part or you have multiple, you're printing them at a rapid stage. Some areas where we're seeing success is you can print sand casting applications, tools. You can print high surface finish parts. You can print parts that behave like polypropylene. High temperature resistant materials are also available. And if you're looking at casting, there's a resin which is really interesting. You can print out this casting part that you can burn away and pour in metal, and you can have your finished part. So this is the SLA. SLA is typically great for rapid printing, design iterations, elastic material behavior. and high detailed surface finish parts. Then we're going to move along. This is a big rep printer. This is a smaller of the big rep. This is a company out of Germany. They print 0.5 meter by 1 meter by 0.5 meter. This is on this studio machine, and then you can do a meter by meter or bigger. And what this allows you to do, this big rep technology allows you to do real size parts that would be really difficult to machine otherwise. Sand casting applications, you can do thermoplastics in this. It's an extrusion-based technology, so you're melting a plastic through the nozzle and it gets deposited. This would be that. So again, different use for this technology, for this big rep technology versus the Formlabs or versus the Nexa. Right here, we're talking about large format printing, so there's a appropriate application for this. Then I'm going to move further along. Here we have the Markforged technology. So Markforged is really impactful in tooling and fixturing and use high strength parts because of their ability to print continuous fibers into their parts, right? So if you're looking for parts that are going to be in the shop floor, they're going to be passed around, they can be knocked down, right? Typically, UV carrying parts are not appropriate for those applications because they're cured by UV and they become brittle. Here, this is the application around tooling and fixturing, right? So your manufacturing aids. Also, I have a metal printer here. This printer allows you to very quickly change out your metal materials to be able to print in materials like copper, hard A2, D2 steels. You can do stainless steel. So a range of different materials that can be printed. It's a 3-stage process. So you print your parts, then you debind it. There's a wax that's holding some of those metal parts, and then you sinter them after the fact. So it's a 3-stage. But again, right application for the right use. This is for that application. Then along this wall here, I have some of the Ultimakers and the Intensys product line. Ultimaker, if you're just, you just want to learn additive, you have no experience whatsoever. You're looking for a plug and play, and these are the type of systems that we see deployed all across different industries. Like, believe it or not, I have automotive customers that potentially, they're printing really large parts. They got these Ultimaker printers because they can print small parts very quick, easier to keep your staff engaged. And you know what? It's a great way. Just like you'll have maybe in your company, you have a culture where you want people to be engaged, and you have a ping pong table. Put a printer there. Let them print something. Let them be engaged in that capacity, and steer their imagination in that range. So that's kind of where we're seeing use case for lots of applications. In Tempsys, this is a technology that prints high temperature, high performance materials. So there's again, right tool for the right job. You're able to print with materials like Ultem, Peak carbon fiber, and very democratized technology. Like if I was to tell you the price of this equipment, you would not believe it. It used to be hundreds of thousands of dollars to be able to print that type of material, but now it's relatively low in price. So the hardware price has come down. So the adoption, is starting to increase. Patents have expired, so there's more and more functionality driven in these technologies. And then I'm going to take you into our production environment. This is a production system. This is by Hewlett Packard. It comes in two sets. So on the left side, you have your material handling station, and the material handling station effectively takes your fresh material, which is in this cartridge, and then takes your recycled material, which is in your external tank in the back, and it mixes that up, and you're recycling 80% unused powder from your previous build and adding 20% fresh. So the recyclability ratio is higher. For systems like this, you don't need support structures because supports are not required. The loose powder holds the parts. This is really a production technology. We're seeing this across the board. You can look at car parts that are being produced, little connectors, harness parts, orthotic parts, agricultural applications, orthotics and prosthetics. I wear orthotics, and my orthotics are 3D printed using this technology and highly customizable, right? And finally, this is the washing station to debind the metal parts from the metal printer that's sitting outside, and then the sintering station to sinter your parts. So all of this, you guys can go in, we try to create it as interactive as possible, so you can click and learn. There's case studies and all that fun stuff. So it's on showroom at showroom.com, showroom.cadmicro.com. Okay, I'm going to switch back the gears. Sorry about that. Mohsen, are you able to see bad photopolymerization?
Yes, it's good.
Okay, fantastic. So here I wanted to show you guys an example. We talked about the liquid resin technology really tackling the speed. And here's an example. Here's 10 different parts, and all with different shape, different complexity. They look relatively same, but there's actually a feature, a design modification in all of them. 37 minutes to produce these 10 different unique parts. That is incredible. In 37 minutes, you can look at these different geometries, make changes, and print them again. This just wasn't possible in the future. It was very difficult to get the speed and the throughput like this. So that's happening. Then the material extrusion, we talked about jigs, fixtures, tooling, right? This is, again, you're no longer limited to square geometries or simple geometry. You can have conformal parts that you can have in your tooling in your sector to be able to use them in your manufacturing aided environment. I'm going to come back to a live demonstration shortly. And then another one is, powder bed technology. And this is what we talked about in terms of the HP guys, where, you got to look at, are there ways to design parts differently? Are there ways to consolidate parts differently? So here's an example of a dual extraction shoe where, it was $450 to make this part, machine this part. Would take you about a week. You had to have minimum quantities. But now you can consolidate this, right? I have this part in front of me, and if you can see in the camera, but these parts, it would be very complex to machine, and they're built upon the generative design concept or design simulation concept. So there's significant ways to reduce cost and go to market quickly. Another part here, here's a company called Square Robot. And they make these robots that go into petroleum tanks, and they do inspection. And for to do those inspections, they have vision systems, and they have lots of different brackets and components. By taking a look at one of those brackets alone, you're able to look at that and see if there's weight reductions and dynamically optimize those parts. You can put them in your simulation techniques, and the finished product was more organic and only designed for that particular application. And all of that, they could test that out relatively quick by going through this exercise. I want to take you guys on a journey quickly and show you capability around remote 3D printing. Just stop sharing again. Okay, so here, this is a cloud-driven platform that I'm at right now. And I'm just going to import a part and sort of walk you guys through this. So this is digital inventory, right? This is no longer I'm working on the physical inventory. This is all digital. If you're working on a project, and you could be anywhere in the world, I'm going to bring in this manufacturing fixture. And you bring your fixture in, this is your tool. It has a conformal shape. It's going to hold a complex geometry that requires boring. You can take this tool, orient your part for best strength. You can apply some process parameter settings. And once you're happy with it, it will immediately tell you, okay, this is how long it's going to take to print. This is going to be your material cost. And you know whether this is appropriate for your application or not. So I'm just going to wait. This is all happening in real time. So it might take a few seconds. So the software is generating a tool path, a G code, and how the machine is going to print and deposit material. Once you're happy with this, you can print this anywhere as long as your system is connected. And I'm going to dispatch this part to our Calgary office, right? So here, this part, for example, is going to take about 11 hours, and our material cost is going to be $16. This is 11 hours while we're sleeping, right? So what we have seen in the market is where there's a great case studies and use cases for these technologies, companies are utilizing more and more infrastructure around multiple printers and smart factories. So we have done something similar. Well, we have offices across Canada. So I have a printer in Calgary, Montreal, Ontario. There's one that's printing in Toronto right now, where I can see real-time data. I can go into it even more in just 53 minutes remaining. But let's send this job to Calgary. And it's literally this easy. I can select the printer I want to send it to. This is my printer. I can add multiple parts if I like, and I'm just going to hit print, and I can say print now or add it to the queue, and that's all it takes. So you're now literally you're sending tangible objects by leveraging Industry 4.0, and it's that simple, right? And here I can see real time. So right now the file is being downloaded onto my printer in Calgary. It's going to start printing, and it tells me, okay, how much time is remaining and so on, and what's happening on the machine right now. So here you can see the plastic temperature is starting to increase because the extruders are now starting to heat up. But the AI functionality is really impressive, right? So what is that? So I'm going to show you a part we printed on April 5th, just a couple days back. And this part here, there's a in-process inspection capability where I can scan my part while it's printing, and I can get data sets around how my part is going to be in real time, and I can look at the specifications. So most of my part is within that 125 micron accuracy, and because of this adaptive learning, next time I print this part, it's going to be even better, right? Because it's learning from this. So this was a long-term missing capability that wasn't part of Additive. You would print your part and then you would go into a scanner, you would scan it, or you would do a CT scan. Now, because of this in-process capability, you can scan and have real-time information inside your parts, which is really powerful. So this is the sort of stuff that's happening. Just looking at the time right now, I'm going to pass it to Mohsen to talk about some of the design aspect. I'm just going to pull up my presentation here. Mohsen, off to you.
Thanks, Deep. Hello, everyone, again. When we look at these design freedom that 3D printing is providing to the manufacturing industry, we would like to be able to engineer that, right? So basically, for example, the bracket that Deep showed on the robot, yes, we can. Today we have this technology that we can make it very light and also very organic shape, but that bracket has other duties as well. We would like to make sure that we can validate that, and also there are technologies based on AI, based on machine learning and optimization, that they can actually give us a product that is light and also organic, and also it is performing the duties that it has. More importantly, it is printable. So next page, please. Now, for example, let's look at that hook at the center of this page. Yes, 3D printing is great, and it's allowing me to make that hook in any shape that I want, as I see here. But which one of these have the strengths that I need, and also like vibration or impact or other performance that they require. So that's one part of simulation that is enabling this technology to be applied better. The other part is that how we can reach to these designs. There is no best practice here. Like, it's not like I have 10 years of experience in designing a hook, so I know what plate or what material I have to use. These are all new, right? So basically we need machines. This is beyond human capability. We need machines to use methodologies to actually give us these kind of designs. And specifically because we don't have a lot of constraints these days. So next page, please. Here is a great example that I like it. So additive manufacturing and generative design, how they are revolutionizing. So let's say if 30 years ago, 40 years ago, if I needed a bracket that provides a hinge point, I would have this legacy part that has 4 connection points, and then I can have a revolute joint there. As we went forward and the manufacturing was more advanced, so we have now, like, let's say the milling machines, like after 10 years or so, like they are more basically utilized. The first thing that happened was that the parts are now smarter, better, right? So, and then using casting, we can see that these days with additive manufacturing, the goal is reducing weight of the components, parts, and assemblies like heavily, right? In this specific case, how I could design that last page, last part. In the next page, we will see it can be even on the assemblies, right? On the mechanism that we are seeing here. Not only we can optimize one part, we are optimizing the whole assembly. And it is very important that, okay, now while I'm designing this mechanism, I want to find the right length of each arm to be able to actually perform the performance that we want. At the same time, I have to be able to work with additive manufacturing engineer to know from all of those methods, FDM, SLS, other methods, like, okay, like while I'm actually generating this organic part, can I print it, right? So I have to be able to collaborate with additive manufacturing engineers. At the same time, this is reducing weight. So we have to be able to collaborate with designers. More importantly, always the industrial design is also important. So really optimization, reduction of cost, time, everything is only possible when all of these are happening at the same time concurrently. And in this specific case, the mechanism that you see, the Dassault Systems 3D experience has been used, which brings that platform that all of the stakeholders can work in parallel: design, simulation, engineers, manufacturing. Next page, please. So this was like for the structures. There are some applications, for example, like jet engine blades or turbo machinery, that really we cannot play a lot on the outer surfaces or in the biomedical area, but we can still do a lot of things inside those structures, for example, with lattice structure. Now, okay, like 3D printing is providing that lattice structure capability, but what type of lattice structure I have to use? Or for example, in the blade, when you see where I need more density for those lattice structures because of thermal effects, because of mechanical effects, impacts, and everything. So this is like with simulation, we can actually design where I need more density and where I can have like less of those. Next page, please. Most of the discussions that are happening around 3D printing and optimization and generative design is around mechanical stiffness and strengths of parts. But another area that we would like to show today is this technology is giving us the opportunity to make advancements in fluid dynamics, right? And we have done similar projects, and Deep in our team has printed parts that shows the ducts, and basically if we have it, probably Deep can show it on the screen for us. like basically, yeah. So you can see those parts. Like these are the parts that not only is improving the performance of fluid dynamics, at the same time, like we wouldn't be able even to think about those kind of designs. And how actually you saw how complex was the duct, right? So this is coming from simulation. This cannot be just by hand calculation. Basically, nothing is now just a straight tube or a cube. I go one step more on the physics, and for the interest of time, we will try to wrap up the discussion around simulation. This is very interesting. Like these days, we have a lot of limitations in electric vehicles, in electronics, that we see. Okay, like batteries are there, but we cannot utilize them because thermal management has some issues, or very advanced and high speed CPUs are available, but there is problem with cooling systems. So really, like I think all of the things are happening for a reason. Like 3D printing is now a solution. Like for example, when I look at the heat sinks here, and this is an example for an LED, you can see like probably 10 years ago, 20 years ago, we wouldn't even think that, okay, the heatsink can be these shapes. And these are like improvements by 50%, 60% on the heat dissipation performance. So sometimes when we hit the wall and the conventional technologies are causing problem, let's say in electric vehicle or in electronic cooling systems, this is the area that we would like to talk with you guys, like our additive manufacturing team and also simulation. So you can see this is important to use simulation for designing these parts, at the same time performance, because this part, let's say if we use a heatsink in an electric car, also vibration, also impact, and also other performance of this component is important. So next page, please. Along the same line, basically, this is another application that 3D printing is allowing that. Next page, please. In this example, I really want to highlight IP as well. So the left optimized part, that is actually a very good heatsink, it's very expensive to build, right? Because we need that accuracy repetitively, and also a lot of aspects with it that are from engineering point of view. The one in the right, that is topological optimized, is not easy to build if we don't use additive manufacturing. Also, because it has its own IP within the design, it can be built anywhere, and also we still can protect the IP. So these are the areas that we see that the technology, if we are not using like these technologies, we might be missing a lot of advancements. Next page, please. And I personally think that in a few years, if I look at under the hood and I don't see these type of structures, I probably will think that that car is not using the current technology. This is not future. This is like something that is available now. Next page, please. And with this page, I want to wrap up our discussion, and basically from simulation in the 3D printing space, simulation will help us to design parts that are organic, that are lighter and better in performance. Also, simulation helps us to have a prediction about the manufacturing process and also performance of those parts. With this, I wrap up the simulation part, and I pass it back to Deep for questions and answers.
Thank you, Mohsen.
Thank you, guys. Yeah, Deep, we have a couple of questions. Do you want me to read them out, or do you want me to? Let me read out the first one. Is the rim on the pedestal next to the Nexa a painted plastic part or an investment casting using a Nexa to print the lost form?
Yeah, a good question. That is actually an FDM part that was post-processed. So it was printed on the big rep, and then it was electroplated after. That's what's sitting there.
Okay.
I'm not sure who asked the question, but when this whole thing goes away, I'd love people to come by, actually touch and feel these parts, because that's where you'll realize the benefit.
And the next one is, so if GM needs a part from sub-supplier urgently at plant 400 kilometers far away, can they start production and not waiting for the next day to wait for the sub-supplier?
Yeah, so another great question. So right now, from my understanding is the OEMs, the Fords and the GMs, they're looking at understanding who has additive manufacturing capability in-house and who has mastered these techniques. So they're vetting out the vendors. How they position that in terms of, printing parts and so on, that's going to be a very interesting model, because how do the files get locked and prepared, and are you going to be able to print only one time and the file disappears? Those are the areas where it's interesting. But to be able to disrupt that supply chain, that is definitely the conversation that we're seeing automotives are having right now.
Thank you. Well, I think that's it. And we are basically at the end of our event. I thank everybody who's joined us today. I thank Mohsen and I thank Deep for an excellent presentation. I know I learned a lot. I hope you had the same opportunity. And I would encourage you to reach out to CAD Micro Solutions for if you have any more questions. Feel free to you can see it on the screen right now. This recording we will be putting up on the website. If you want to share it, it'll be there available in a couple of days under our events page. So thank you again, and have a good day. Oh, one more thing, if you're all interested, NGen has a pavilion next week at Hanover Messe that includes some live streams about certain companies, and we invite you to take a chance at visit. We have visitor passes available. So again, I want to thank everybody and have a great day. Bye-bye.
Thank you.